Yes, so long time no see. I hope you have been working hard with your first exercise. Yeah, so it has been some time, so just to recap what we have done so far. So in the first class, I showed you like the field development process, right? And then we went in detail, which was a bit heavy, to see which kind of tasks were done in each step. Okay, how does it look like? That's how it looks like with the diagram. And we put some terminology that some companies use. Remember, this is not used by every company, but most of them, they have these steps and they have these decision gates in these positions. Okay, and then we saw a bit what kind of tasks each phase had. Okay, and I told you now you have an exercise. It's about the Hebron field in Canada that you have to make. Okay, and I will show you now the description. Where is it? But that you have to go inside, and rather I tell you the story, you have to go and read yourselves, and you have to find out what kind of tasks one have to make in this video. Okay, but basically the main idea is that you have to go within all of this process. You have to define first, have an overview of possible ways to develop the field. Okay, to define all elements of what I call, and I'm going to show today, the value chain of the reservoir, how I'm going to deplete it. You have to say which offshore structure I'm going to use, when are you going to drill the wells, what's going to be the completion and the layout of these wells, the offshore structure, the logistics, how I'm going to transport this oil to the market, what kind of personnel I'm going to need, what kind of operations I have to make, etc. All of that. And then I have to go and progress, and I have to discard all of those options that are less attractive. Okay, and for that I have to use an indicator. Until I get at the PDO, I say, well, after all my homework, I have to give to the authorities, and I say, well, that's the best we found. Okay, that's the best alternative we found. Okay, and after that comes the really the hard work, where I have to go in depth in each one of these, each alternatives, and not alternatives, but each one of the parts of the chain and value chain model. You have to go and actually do the detailed design of every small piece that is going to be in that offshore structure, in the reservoir. You have to go and do the analysis. Yeah, and I think that's what we did so far, and we reached up to operations. So I told you on Blackboard that you should watch these lectures 2 and 3. So my intention now is I'm going to cover very quickly the content of these lectures in a very summarized way, and I will try to give some more things that I don't normally teach in the course. Okay, because I assume, how many of you saw the lectures? Not many? 1, 2, okay. Well, I will go very quickly through what is covered in these classes, and I will give also some additional things that I don't normally mention. Okay. Then some things that we had pending. I remember I told you that we have these guest lectures. Okay, and we got already a kind of a tentative schedule. And these lectures are going to happen not in this room, because we're going to get also students from another course, from the energy department. Okay, so we are not going to feed all of us here. So it's going to be in P13. I think it's that one on the left. Okay, and there will be from 2:15 to 3 on Mondays. Okay, so yesterday. And you have to, in order to get access to the exam, so you have to sign the sheet, and you have to be at least attendance 50 or 50%. Okay, of I think there are maybe 10, so you have to go to 5. Okay, at least. Yep. So, and the intention is that to give you an incentive also to be in the lecture. Sometimes one might feel a bit lazy, I don't go, but this is people from the industry that they take their time and their resources to come here to give you some very useful information, some more practical information. So I think that's a good way also to not to force you, but to give you an incentive to go to these lectures. Okay, so keep it in mind. So next one is next Monday on this room from 2 to 3, and then we resume normal classes here from 3 to 5. Okay, so hope to see you there. And the topics of the lecture, of course, the other course is on multi-phase transport, so they like a lot to talk about flow assurance, but you will see things that you have to do with operations, you have to do with subsea processing, so some things that are also relevant for our course. Any questions about that? No? Yes, I think you're still sleepy, so. Okay, so remember next Monday, first lecture from 2 to 3, P13, and then we come here, 3 to 5. And yeah, and you have to come at least to 5 to get access to the exam. The other detail was that we had, so the session for the exercise, okay, I think that the assistant is going to take care of it. Martin, that I showed you his picture. I think he's not here today, but so he's going to take care of organizing the exercise sessions. Okay, but I think most of you send feedback on the link. Now there was one question from one of the students that I think was last time we saw each other, that she said that she was from the gas engineering program and she had to walk, from Glos to here and then back for this lecture. So she asked for the option to if we could move the lecture hour. Okay. So the result of that questionnaire is shown here. So there is something strange. It's something that happens, in some countries. You have some people that vote many times. I think here we are like 40, but you have some ghost voter that goes, and so we have some corruption issue here, okay? Because we have 75 votes. And we can say, well, it's a failure of the system, the voting system is faulty, so somehow a vote gets recorded more. We are not going to exclude that option. But, so it says here that it's Tuesday, so this today, okay, from 12 to 2. But I think this lady, she had also in the gas engineering, the students from the gas program, they also had another lecture, right? From 12 to 2. Is it? Yeah. So that doesn't work for you, this option, the most popular option. So I suggest we keep it the way it is, and we'll, you have the video lectures. We also wait a bit for you until 2 minutes after the time, but we hope, you manage. I think there is not such a big issue, okay? If that's okay with you. So we keep it the way it is now. Yes? All of you agree? Any big, no? Objections? No? Okay. Yes, so let's go so today I want to talk a bit about abandonment, okay, and decommissioning and abandonment. I told you that this is something that you don't normally, yes? Yeah, 2 to 3, I think. Let me check. Yeah, 2 to 3. Mondays, 14 to 15. Is that correct?
Every lecture is going to be the same time?
Yeah, the same time. Okay. We can talk later. If one of you has a very big problem especially these students from other programs, not from petroleum, please send me an email and then we can discuss it and we can find out if we can record it or do something, okay? But just send me an email, okay? But why you have, because if you're from the gas program, right? No? Okay. So you don't have this non-collusion...
On Mondays I have class from 2 to 3.
Okay. Yeah, because usually when you have some course that is mandatory, they make it that you don't have any conflicts with the other courses. But this is something that you're taking optional, like, okay. Yeah, so we send me an email so I know your name and we will try to find a solution, okay? Yes. So today we are going to, abandonment, I mentioned, is usually very much neglected, okay, because it's not fun for petroleum engineering, or to talk about after you put the equipment, you design it, then I have to remove it, okay, I have to scrap it. And you think, well, that's very boring, but really it's a lot of science, and there are a lot of things that you have to know for doing that process. So yes, so I'm just copied here, so I will go very quick. Okay, the commissioning, basically after I say, well, it's not longer profitable to continue producing, or I have produced already, I have reached my goals, I have reached my recovery factor, and I'm not, I'm operating in losses. Okay, then I start and I decide, let's do the commissioning. Okay, and the commissioning usually it's the way we say, well, we plan the field for example, a life of 20 years or 15 years or 5 years, but then after I reach a certain economical rate, below that number, I just stop production. Okay, that's usually how it works. And then I have to start doing all of these tasks that, I have to do what is called engineering down and clean. That means that I have to remember there are hydrocarbons. After I shut down the system, I have hydrocarbons in most part of the system. So I have to do a flushing, cleaning, processing equipment, cleaning all the processing equipment and piping. And these hydrocarbons, it's not like they go and I have to dump them or something. I can sell them. Okay, so there is still quite a lot of money when I make that flushing and cleaning inside the system that I can recover money from. Okay, then I have to notify the government, and I have notified the relevant environmental authority to say, well, I'm going to shut down the field, just that we can coordinate measures, if something has to be done together. Then one of the main activities that is extremely expensive and extremely time consuming is well plugging and abandonment. It's not that I can just close a valve in the Christmas tree and then I go and then I forget. I have actually to create a barrier in the well such that I guarantee that there will be no leakage of hydrocarbon whatsoever to the environment. And this is, we are not going to, maybe you're going to cover it some other course, but basically I have to remove the Christmas tree and I have to remove the tubing that is inside the well, and I have to put a plug, a cement plug. At least 2 of them. And this is it's almost like drilling. You have to move a drilling rig, you have to do a cement operation, you have to retrieve the tubing. So this is all I need for this process. I need a drilling rig. Yeah, and it's extremely expensive, but has to be done. And on top of that, it's not only sufficient that I plug and I say everything is fine, trust me, I give you Milan's guarantee, but also you have to do monitoring. You have to do somehow to monitor that after you have plugged the well, you don't have any leakage in the area. So you have to monitor hydrocarbon concentrations, and that also, it's something that is costly. Okay. And after the well is plugged, then you have to remove the well conductor and the casing. The well conductor is the outer tubular that holds the whole weight of the well. Okay, the well of the weight of the Christmas tree, the well of all the casings, the well of everything. So the well conductor and the surface casing, they have to be cut and removed down to, I think it's forgot the number now, but I think it's at least 3 meters, 15 feet below the sea level, not the sea level, the mud line. Okay, the sea bottom. Is it 3 meters? Any of you remember? Yes, I think it's 3 meters. Okay. Then after that, of course, you have to leave the sea or the surface the way it was originally. So you have to remove all topside equipment. And here there is actually, a lot of also money to be made, because many of these equipment, remember, we have pumps, we have separators, we have compressors, we have generators, we have all kind of equipment that maybe they can be reused in another application. Okay, so that there is a big business in taking this old equipment, dismantle it, but then selling the parts that are still useful, that still have a remaining life. Then the most costly is the removal of the offshore structure. Okay, and there are some structures, for example, we will have a lecture just separate on that, but if it's, for example, a floating structure, an FPSO, it's very easy. You just have to, ship it or sail it to some other place. But if it's a fixed, okay, if it's a jacket or something, then it's a big job, okay, to disconnect this jacket, lift it. And sometimes authorities, depending how difficult it is, they accept if you, don't remove the whole thing, but if you remove down to certain part. You have also some other structures which are based of concrete that are a pile, and these are also extremely difficult to remove. Okay, you have a bunch of tanks around, so sometimes the authorities, they say, well, you remove the surface part and then the rest you leave it there, and we have to put, of course, we have to signal it during the navigation maps, so no other boat is going to crash with it, but we allow it, but that you have to ask to the government. Okay, then another thing is that you might have, remember, subsea pipelines, if you or onshore pipelines, that you have to remove them, or some cases it's accepted just to bury them, to dump, okay, sand on them. Mark, that is what I already mentioned before, leftover installations on marine maps, such that if you have a fisherman boat or don't get stuck on that on what is left. Monitoring, extremely important. You have to monitor that, hydrocarbons, how is the evolution of what you left there, if it's non-changed, and disposal of residues. Okay, that's in a rough way that are all the activities that are involved. And I don't want to spend too much time on it, but I highly recommend you to go to these links, okay, and watch these videos. If you are bored, like I told you, if it's Friday night, you don't find nothing to do, you're bored, no parties, no nothing, so you go and watch these two links. Okay, they give you a very good overview, and regulations change from country to country, but at least you get a view of what. And in some of you, wants to make money on that, then I think we are going to have in the future, and we have already started to decommission in the North Sea, Norway, all of these structures, okay, and all of these wells. And it says that it's going to take a huge amount of time to just plug and abandon these wells. So we need also engineers to focus on that. Okay, so these are the two links. Okay, any question on that? No?
So who's going to monitor the well after it's plugged?
The monitoring depends on but for example, you might put some cameras, you might go and regularly measure the surroundings, the area surrounding the wells, to see if you get some hydrocarbon measurement. It depends. You might use, for example, boats to sail every once in a while. Okay, so it depends what actually you're monitoring, but usually you're very concerned about hydrocarbon leaks from the wells, and also on some other on the structure that you left on the seabed. Okay.
Okay,
Yeah.
but who is going to monitor it? And the government or the company that has the
That's
permission
also a bit complex. At least here in Norway, the government pays for a big chunk of the plug and abandonment cost. Okay, but usually the company has to pay for it. It depends on the country, but the company has to pay, but the government, it has to take the big how you say, the big expenses, has to pay the big expenses. Okay, but sometimes they tell the company that they have to be in charge of managing the monitoring. Okay, so they are the ones that design, that devise everything and follow the regulations. It's not the government themselves that they go and they plug the wells, they go and do everything, but most of the cost is paid by the government. Okay. Any other question? Okay, now we go. I want to, just before we go on the technical part, it's like Yeah, because we are going to go much in detail later to see how do you estimate how does a field behave. Okay, now we're going to talk about field performance. Okay, and that's just the production performance of the field, and we are going to talk much more about that later, and we are going to see how to make calculations, and I'm going to say, well, the different approaches that you use. But this is like a thought experiment that I think is very useful, just to to understand how the field works, and more importantly to see that there are two main production modes, two main ways in which I can produce this field. Okay, that you have to have very clear from the beginning. And the best way, I think, is to use a very simple analog of the production system, and then we can make expand the discussion and discuss other things. So there are two basically the field I can use. Let's make a simple analog of the field, and I'm going to say, well, the reservoir is almost like a tank, right, where I have hydrocarbons inside. It's a tank. So I say, well, my reservoir is just the tank. Now, I'm a mechanical engineer, so I like tanks, pipes, things that I can grasp. So I say that's my reservoir, and the reservoir just has some fluid inside and has certain reservoir pressure. Now, if I go from the reservoir, now I'm going all the way to the bottom hole. Okay, I'm saying, yes, remember, I have the tubing, I have the casing, I have here someplace this famous reservoir pressure, and then I have a flow, and then I reach that point, and maybe we should make that drawing a bit better. Okay, so I'm going to first paint that, and these points you have to remember. Okay, no matter when you wake up here 20 years from now, you wake up in the middle of the night and you have to say reservoir pressure, bottom hole pressure, and more to come. And we're going to make a very simple, let's say that is a single well. Okay, but all fields, more complex, less or more complex, are going to behave the same way. So you have here a separator, and I'm going to say that's P separator. Okay. Then that's PWF, that's bottom hole flowing pressure. And then someplace in the formation, I'm going to put it nice. Someplace here you have reservoir pressure. And you have another big point here that is called PWH, and that's called wellhead pressure. Okay. And also we have another element which is extremely important, and that we have in every reservoir, in every well, in every production system. That is called the choke. Much easier to okay, that's what I call the choke. Okay, so remember, I have reservoir pressure, bottom hole pressure, wellhead pressure, and separator, and I have an element which is the choke, okay, that I can regulate. It's like a valve. Let's call it here at this point that is a valve, like the one you have in your house. So if you think about the system, to come from here to here, I will have a pressure drop, right? And that pressure drop we normally call, petroleum engineers, we call it drawdown, right? But in my analog, I say, well, that's a tank, and I'm going to put here a restriction. Okay, from reservoir pressure is like a place where I have a restriction that I have to flow from there to PWF. Okay. Then from that point I have to flow through the tubing. Okay. And that we have different, we are going to see later, but one of them is called the tubing performance, okay, on the vertical lift performance, that I have to go from bottom hole all the way to wellhead. But that I can also say, well, that's, I can put like a fixed restriction. And here I have P wellhead. Now, here comes a big difference, okay? The choke, I might have two types of choke, and we're going to discuss it later. But one choke is one that I can adjust, okay? I can move up and down. But I have another type of choke which is fixed. It looks just like that, just like a restriction. So I'm going to say for my example that the choke type we have is a choke that I can adjust. I can take up and down. Okay, and I have a place where the choke sits. Okay, so that's my analog of a choke. And then I have, again, I have another restriction that will be the pipeline, right? And finally I have another point here which is P separator. Okay, so that represents the pipeline, this represents the tubing, and this represents the formation, or we also call it the drawdown. Yes? Yeah, so that's something very important to say. Pipeline, tubing, drawdown, they are usually fixed unless something happens. How can they change? Okay, how can these restrictions change? I ask you now. Are they going to change or not in this analog? For example, let's say we have the deposition of something called scale, okay, in the tubing. That in the tubing we have that the walls are going to become smaller and the diameter is going to become smaller and smaller because you have accumulation of something on the wall, okay, on the tubing wall. In that case, that restriction is going to change, okay? But it's going to be a gradual process with time. Or the same thing can happen on the pipeline. On the formation, if you have, for example, some kind of formation damage, okay, something that affects the permeability of the formation. So they can change, and usually it can be dramatic, okay, it can happen one day to the other, or it can also happen gradually. It usually happens gradually with time. This is very different. This is something that I, at will, the operator of the field, I can change, okay, move it up and down as I wish. Okay, so that's, roughly my production system. And I have, so let's put here, I have, so that's the mechanical analog, or the simple analog of a field. And I can operate in two ways this field. So first I ask you, how, remember that we say the rate, okay, Q, that can be of oil or it can be of gas. Oil if it's an oil field, or gas if it's a gas field. And I remember I told you we got the convention that oil with a bar on top, that means, what does it mean? Standard conditions, okay, and G as standard condition. For those of you not coming from petroleum, sounds a bit crazy that, these guys talk about volumes. Volume depends on pressure. We should talk about kilograms. But that's the way it is, okay? It's because it's easy to know how much money you're going to make. If you already have the volume, you multiply just by the oil price, and then you get how much the field is going to make. It's a bit weird, but that's the way it works. Okay, so I'm going to ask you, this rate that I have, it depends on what?
Pressure drop.
On the pressure drop, okay? choke opening, but let's just wait. In first principle, okay, it depends or is proportional to the difference between PR and P separator, right? That's the driving force behind the rate, right? And now I can change that. If you see that this PR, you know, I have, so what's going to happen with separator with time? The pressure of the separator?
Constant.
Constant. Why? Well, one simple reason. Separator, remember, we are having volumes, okay, of liquid and gas, right? So if I change the pressure, these volumes are going to change. Okay, if I put the pressure much lower, the volume is going to be much higher. And the velocities here are going to be, for example, not like that, but they are going to be something like this. Okay. And then the deposition of the droplets in the separator is going to change dramatically, completely. Maybe they won't have time to fall, you know, to fall at all. Okay, so that's very careful. This process is very careful, and this is like a religion. Okay, P separator, that's fixed. I try to keep it fixed. That doesn't going to change with time. Okay, just because of many things, but one of them, separator, compressor performance. If I change that, that's going to affect the whole thing I have. Remember, here I have something called processing facilities. Okay, and these processing facilities, they are happy, extremely happy to have a constant pressure, and they would like also a constant temperature, but that cannot always be guaranteed. So they are happy with, keep me that fixed and I will be out of trouble. You start changing it, then, you know, I cannot guarantee I'm going to operate successfully. But then we have the other part of this equation, that is reservoir pressure. And what's going to happen with time, with that pressure? It's going to go down. Why? Because we are taking material out of this box. Okay, we're taking, because of the production. This pressure, if we put it in a very simple way, is a function of NP, right? Or GP, which is, if you remember, NP is the integral from time 0 to time t, okay, t star, let's say, of Q dt, right? This Q oil, or GP, will be Q gas. But there is something else. So this difference is important, but also you have, well, this difference is just the pressure drop. Okay, this is equal to the drawdown, right? Plus the delta P of the tubing, plus the delta P of the pipeline. But you have here something extremely important, which is the delta P of the choke. And this I can control. Right? So that depends, this difference in pressure depends on this pressure drop, this pressure drop, this pressure drop, and that pressure drop. And none of them I can control. Only the choke. The choke is the only one that I can control how much delta P. And by doing that, I'm going to control the rate. That's the only way I can control the rate. Okay, so let's, now that that's clear, I want to say the operating modes of a field. Okay, that's really what you have to take from this discussion. Operating So I have two modes. One of them is constant rate, operating, or also called plateau mode. And I will going to call this mode A. And I'm going to take, you know, you will have to make it again, but I'm going to take the same figure. Sorry. Okay, but I'm going to say, well, I will put here in this location something called FM, and this FM stands for flow meter. Okay, and that's going to measure just how much rate I have, how much Q I have. And then I'm going to give that back to a controller. Okay, that's going to be C, a controller that is going to go back to an actuator, and automatically it's going to change this opening, okay, until I get the rate that I want. And the production profile Remember, production profile is declining? No, it's constant. Yes? Because I'm forcing it to be constant. Okay, I'm saying with this choke, I'm going to forcing it exactly to be, let's use exactly constant. Okay, and this is a bit difficult. So initially, let's think a bit. So initially this choke, let's say I want a rate, okay, a rate which is, if I leave it open, no choke, right, I will have a rate which is very big. So I want exactly a rate that is lower. In that case, I choke, right, and I close it very much until it's extremely close to the seat. But then what's going to happen with time? For example, another time 2. That was at time 0. What happens at time 2? At time 2, that pressure has decreased, right? So the maximum rate that I might have is going to be lower, right? But to keep the same rate, what I'm going to have to do? To open the choke, right? Is that clear? Because just because that pressure went down with time. Okay, so in all of these steps, in all of this time, and that's something extremely important for this mode A, I'm going to have to adjust the choke, open it. If I don't have this magic thing, okay, that is controlling it, I have to bring a person physically, and that person has to open the choke every certain time, okay, every month has to open the choke. Now, what happens at some point, what's going to happen here? Well, fully open, right? I have reached the upper limit of the choke. So at that point, and that I call the end of the plateau. Okay? And at that point, I lose control of the field completely. Okay, I cannot control anymore how much. Here I was controlling exactly how much I can produce from the field. But at this point, I lose control. The field operates by itself. Okay, this decline I have completely no control on that line. How is it going to decline? Okay, so just the learning is that, keep in mind, I'm not able to keep this plateau rate forever until the choke is fully open, and then it starts to decline. Okay, so I also want to show there is on my website there's a very simple field simulator, okay, that has exactly the same system. Has a reservoir, has a tubing, and then has a pipeline and has a choke. Okay, and here you can regulate. Actually, it's made to play that you can regulate how do you want the choke, how open. This is closed choke and this is fully open choke. So before doing that, I'm going to copy that link. Okay, and I have to put some data to see, you will see later what is that, but that's basically initial reservoir pressure. That's how it's going to drain with every cubic meter that I take out of this tank. It's going to decline in, a fraction of a bar. This is the resistance, that restriction that you had for the tubing is representing that restriction, also this one. And this is the days that you have, the number of steps and the days that you have. So here we're simulating 20 years, and that's just to show how quick it's going to, and 7 wells. Okay, so let's make an example. Let's say first I want to operate the field here. Okay, so you see exactly I'm producing that rate, and if I keep the choke fixed, that's going to start to decline immediately because reservoir pressure is declining. So let's see what we discussed now. What will I have to do to keep the rate constant? Okay, so I have that. I I correct again, I correct again. Okay, correct. You see it's not exactly smooth. Okay, I put a very perfect line, but that's something also that you have to take into account. Operationally, I never have an exactly flat okay, but it's going to go up and down because I have to be opening and opening and opening the choke. So when do we use this production mode? Okay. Usually is used in standalone developments. That means field that I'm going to make its own processing facilities, its own production structure, offshore structure, that I have to build everything from scratch, that I cannot use any neighboring field to produce. Okay, and why is that? Well, because if I design, for example, all of this processing train that is here, right? I designed that for a rate. Okay, I designed that for this rate, and it's really not very economical if I, and if I, for example, if I produce like that, okay, I design my processing facilities for something like this, okay. I will be using the facility. I imagine I built $1 billion facility to take a very big rate, this initial rate, but I'm going to use it only for the first second of the first month of the first year of production. And then that's it. I'm never going to use it anymore at that rate. Okay, and I spent a lot of time and money to build a big separator, big pumps, big compressors that can process that rate, right? But after that, I don't use it anymore. So it's like money not well spent. So that's why I prefer to operate at a constant rate. So let's say here standalone developments with independent processing facilities and offshore structure. And usually it's a new fields, okay, with no neighboring fields. Okay, it's already 11, so do you want to take a break? You need a break? 15 minutes? Okay. Okay. Okay, so keep it in mind, mode A is constant, okay, and I have to be opening the choke, and of course that is a very kind of illustrative example that it's not simple to keep it constant. Okay, you have to regulate up and down, so you're going to be around the plateau, but and then there is another mode which I'm going to call it as B. So it's a pressure decline mode. Sorry, constant pressure. Okay, and I'm going to take again the same system. But now I'm not going to measure the rate, but I'm going to measure actually the pressure. Okay, the rate. I put here a pressure gauge. Okay, I put the same controller that I have here, and then I have an actuator Okay, and I'm going to be sure that all the time I operate P wellhead pressure constant. Exactly the same arrangement. Now I ask you, what happens if the pipeline is very short, is extremely short? This pressure is going to be the same as this pressure, right? So if you want that pressure to be constant, okay, you can say, for example, that will be equal to separator pressure. That means fully open choke all the time. Then the controller doesn't have to do anything. Yes? So the rate in this case, it behaves versus time. Here I think I forgot to put time, right? Behaves just always declining. Okay, always declining. And here it's again the same thing applies for this case. If I have a very high rate initially, remember here the rate is a function of the difference, or is proportional to the difference between PR minus P wellhead, right? Because now it's wellhead the one that is fixed. Okay, and PR is going to go down with time. So in consequence, Q is also going down with time. And that also has the consequence that I have to have something to process this rate. These very high initial rates, I have to have something to process that rate. So for that reason, usually this is used for satellite wells, for satellite field, producing to an existing facility with spare capacity. Okay, typically. Remember, if we think about the economy, is usually always from the point of view of revenue to have the highest revenue or the highest production as quick as possible. Okay, so if you think about in a very cool way, just saying how I will get the highest revenue is just producing the fuel at its maximum all the time. Okay, just fully open choke. The problem is that I will need for big fields, I will need two big processing facilities. Then the capex will be extremely high, and then that will make the project non-economical. Okay, the capex will be extremely high. So in this case, we produce only satellite fields. For example, we have a neighboring field that has produced in plateau, a big field. Okay, and it started to decline, and now we have, at this point in time, we have this much production capacity. Okay, that we can say, well, if we have a satellite, a very small field that produces with this profile, I can actually produce it connected to this other field. So this is a field 1, okay, and this is a field 2, and this field 1 is standalone, and this field 2 is satellite. Okay, so I can decide at time t, well, this one has enough processing capacity that can take the production from the satellite. Okay, well, actually that won't be like that, but will be right, and the production starts at t star. Okay, so that's Q versus time, and then I can recover as much as possible, as quick as possible. And ideally, I would like to produce every field like that, but it's not it's not possible as much. So we say
Excuse me?
yes.
Just the star what mean for us? I didn't
Well, T star is when the T star is the production startup of the satellite field. Okay, production startup date of the satellite field.
You mean after this time our standalone field become satellite field?
No, no.
That's meaning?
No, I'm saying you have here you have two neighboring fields. Okay, you have, let's say, here you have the standalone field, a big field that has been producing for quite some time. Okay, for 30 years. Here you have a horizon of 30 years. Okay, and you made a discovery of a very small field that is only, so that's a satellite field that is only, for example, let's say 15 kilometers apart. Okay, and you say, well, I could build an offshore structure, I could build the processing facilities for that field, okay, and then I will have to produce it like this, okay, plateau and then decline. Or in this field, at that particular point in time, okay, it's already declining, it's out of the plateau phase. Okay, so I have spare capacity available to take that production. So I will say, instead of producing that, delaying production, I will produce as much as I will connect it to the standalone field and produce as much as possible. Okay? That clear?
It's tied back, isn't it?
Yeah, that's it's called, yeah, the tieback.
Okay.
Tieback. So the satellite field produced okay, remember these two production modes, and you have to remember also a field produced in mode A is always going to end up in mode B. Okay, mode A always goes to mode B. Yes? Any other question? No? Yes?
I mean, I'm just a bit confused here, because if you tie into the existing facilities,
Mm-hmm.
you think like you need some constant rate and not just control like wellhead pressure, because it just you are bound by the capacity of the other thing here.
Well, this field, for example, I say I produced it 20 years ago, okay? And has been producing with constant rate, because I have to build its own platform, its own separator, everything new, okay? But then after, for example, let's say 5 years ago, it started to decline. Okay, 5 years ago it was here, and now it has, let's say, it was built initially for 1 million barrels, but now it's producing 700,000, okay? So let's say this plateau rate was, well, let's use North Sea numbers, which are 100,000. And now is, for example, I don't know, 70,000. Okay, that means that I have an excess capacity that I'm not using of 30,000 barrels. Okay, this small field, if I leave it, for example, with open choke, okay, it can produce, let's say, 22,000. Okay, but that, if I have to make a facility for that rate, okay, and for that volume, it will be extremely expensive. A new facility, a new separator, a new offshore structure. So I decide, well, this field has 30,000. So I decide just to put a pipe, okay, not to put any processing facility, any offshore structure. I just put a long pipeline, 15 kilometers to this field, and that field has enough capacity to process it. And then I can produce as much as possible, as quick as possible. And I don't have to wait a long plateau to get revenue. Yes?
Would you have to change something in the processing facilities if the compositions are different from the
Yeah, that's also some other, also flow assurance. There are all kind of issues there, but it's in a very simple way. Here we're talking just on the production mode. Okay, But you have to be that the fluids are compatible, that these 15 kilometers I won't have any wax deposition, I won't have any hydrate problems, etc. But that's for another day. Okay.
So this means we increase our production in satellite fields. That's all.
Yeah, in
Depend
that
on our spare capacity.
and that means I'm able to produce this field. Maybe it's small enough that if I were, for example, if that field was in a very remote area in the north, maybe I won't be able to produce it. Okay, it will be so expensive to build the offshore structure, to build that I won't be able. It's too small to be economic. Okay, but because I produce it to a neighboring field, then I'm able to make it economic. Okay, I'm able to for it to be economic.
Excuse me.
Yes.
I missed the part when you said what they usually end in the. Can you repeat?
Yeah, this is exactly this point. Okay, that. Remember, I for operating in mode A, I have to open the choke every year, okay, or every month. Open, open, open. But there will be a point where the choke is going to be just fully open, it doesn't rotate anymore, okay, the valve. And in that point, when that's fully open, the system is just going to be, the rate will be given only by the difference between reservoir pressure and separator. And reservoir pressure will continue to go down. That means that the rate will start to go down. I appreciate, what you, sometimes I go through a very simple example, trying to clarify the discussion, but sometimes I confuse you more. So I appreciate that you force me to make it proper, to put, more numbers, nomenclature, etc. So, thank you. Yes. So just to show you, so you can go just also, if you are bored, you will have to do it maybe later in the future. But the NPD, the Norwegian Petroleum Directorate, and you go to, I think it's called Facta, let's put it in English, fact pages. And you go to field, and I think you go to production. Okay, and you have all the fields in the North Sea, Goliath for example, and here production. Okay, on the left, production monthly by field, and you can get exactly, it's very open, so you can get exactly what each field is producing. Yeah, and you can plot, if you are bored, you can go and plot the production profile of each one of these fields, and you can find, which one was in plateau, which one was satellite, etc. Okay, with time. I also have on my website, let's see, I think it's here in files, is production, I did it April last year. So you have here a utility to visualize. So it has the same data from the NPD, but you have, see if it opens, and it's available for everyone to download. Wait. Okay, also Veric, Ormen Lange, for example. Okay, so here you have, that's rate of oil, rate of gas, I think is the one in, can you see more or less during the first phase that was operating, and as I told you, it's not going to be, sometimes you have problems, some months you have to shut down some wells, you have to do maintenance, but more or less it has remained constant up to that point. So it started decline more or less in 2014. Okay, but first, and initially you have a phase. How do we call it? We discussed it last. Okay, the ramp up, and where we start putting wells in operation, and then you have variation, but more or less is like a plateau production. Okay, and you can find here has exactly the same. So I will put the link in case you want to have some fun. Okay, and I think I have some examples. There is a website which is quite interesting that the person is trying to make an analysis of different fields and try again. You see the decline because many things happen during production. It's not exactly smooth, but if at the end on the overall data you put a trend line, actually you have that decline. Okay, you have here a field that has a plateau for a few years. Okay, actually quite a few years, from the 80s all the way to 90s. Okay, 10 years, and that's oil, this field, and then you have entering to decline. And you have some other field who actually had a very quick ramp up, and then so this is probably a satellite field. Yes. And here we are talking specifically on on offshore. Onshore it might be because you always have neighboring field, so it might be that you try to produce it like that. Okay, unless it's a very big field that you need to build something new from scratch. This was taken from. Let me put the link here if any of you is curious. Okay. So just to also tell you that there is a relationship, or let's say a very close relationship, between plateau, we call it height, okay, and plateau length. Okay, I might produce, for example, the field in the two following streams. Okay, I can say I want a very low rate, right, and then I will take years and years and years until I reach the plateau end. Okay, and essentially enter into decline. Or I might produce, for example, medium, and then I enter quicker into decline, higher, okay, until I reach, let me put it a bit lower, okay, until I reach the end, the other extreme, which is I produce completely in mode B. Okay, so I have a relationship. They hired, and you think that, okay, like intuitively we will see now why that comes, but intuitively, if I have the higher the plateau, the shorter is going to be. The lower the plateau, the longer is going to be. So how do I take that decision of plateau height is defined or is determined by performing an NPV analysis. Okay, that we are going to see. I don't think we will have time today, but on Monday. Okay. So higher plateau, I will have higher capex. Okay, is capital expenditures. Is everything that has to do with offshore structure. Okay, we're going to look at that later, but this is the offshore structure. This is the processing facility. These are the pipelines, etc. Also, you have higher drillex, because, well, to produce a higher rate, you're going to need drillex is drilling expenditures. So you're just going to need more wells, right? So this doesn't look positive for higher plateau, because you have higher capex and higher drillex. Okay, but also you have what we say quicker and higher revenue. Okay, not only that, you're selling, if you're here, you're selling initially a big amount of oil that you're going to get a very good revenue, but it's much, you see we have something called is inflation. Okay, we have, so it's not the same to get $1 here that to get $1 in 20 years. Okay, because we have this inflation phenomena in which the money is not worth the same every year. Okay, you have that it loses its value. So if I get the money, sell it very quick during the first year, it doesn't have time to lose value. Okay, it doesn't have time to lose value. So quicker and higher revenue. So these are two things that are like in a balance: the expenses and the revenue. Okay, and lower plateau is just the opposite. Lower plateau. So here, let's say, I should put it below, I think. Lower capex. Okay, also gives you lower drillex, but it also gives you lower revenue. Okay, or delayed revenue also. Delayed revenue. So it's like you have a balance. If you put these two things, you have in a balance, you have, okay, you have the revenue, and then you have the expenses. Okay, and you have to find a point where I can maximize my revenue and minimizing the expenses. And that I can only make by making sensitivity analysis. So the plateau height is usually defined or found by performing sensitivity analysis. That means I have to try with different plateau numbers. I have to calculate my revenue, I have to see what are the expenses, and then I have to calculate the NPV to maximize NPV. And you're going to get an exercise on that in the future. Okay? But also keep in mind that plateau height is usually something I can decide upon. Okay, I can decide bigger, smaller, okay, as long as it is the limit. I have an upper limit, which is the open choke value. But then below that, I can choose basically any number, right? I can decide, and I will find with this NPV analysis what is the most attractive. But something I cannot decide, or I have completely no control, is the plateau duration. Okay, is defined or is given by physics. Okay, just by the physics of my system. It's a natural limitation of my system. Okay, I cannot control. If I define this rate, then I will have a plateau of 30 years. If I define this rate, I will have 15 years, and so forth. That number I cannot control. You see, we will see later in the course that there are some measures to try to prolong a bit the plateau. But that's given by the system. That's a limitation of the system, and I have to live with it. So here it becomes extremely important to do a proper forecast of the production profile. Okay, it's extremely important because I can say, well, go for it. Okay, I think if you choose 100,000 barrels, you're going to produce for 30 years, and you make all of your economy, you develop the field thinking that, and then the field after 10 years starts going down. Then, they get rid of all of these reservoir engineers that were in the planning phase. You cost a lot of money, lose a lot of money. So this one, we are going to dedicate some time to make it right, and it is extremely, extremely important. Okay, some more comments on that. We have also something called production scheduling. Okay, that is define the rates of the field and of each well during the lifetime of the field. Okay, that is defining, well, if it's very simple. Mode A, I know is constant and I have to decide the plateau, and mode B is just decline. But remember, this it's a very complex system with multiple wells. Okay, the same thing that applies at the field level, now we go and we can operate the same way in each well level. Okay, so I have to decide how much each well has to produce. Okay, and that also we call it reservoir management. Okay, that is to define how much each well will produce. Okay. And to keep, for example, you decided, well, my field is going to be producing plateau, but maybe the wells, they might not be producing plateau. You might, for example, start with some wells that are declining and then some that are choked, and then you open the choke on these wells and you start, the others, while the others continue to decline. So you have to decide. It's a very complex process, especially when you have many wells, how to produce the field, what to produce from each well. And keep that in mind, okay, that even the field might be in plateau, but inside the wells they are producing in mode A, a combination of mode A and mode B. And you think, okay, what defines how much each well? So there are many things, but for example, like reservoir characteristics. Okay, like for example the productivity of each well, simply because the reservoir is not homogeneous. Okay, it's heterogeneous, so you have wells that have different productivity. You have, for example, some wells are closer to the water oil contact, some wells are closer to the gas oil contact, so they can start coning, gas coning and water coning. So gas, water coning. You have also sand production. If you produce too much or at a high rate, you might affect the stability of the formation and you start getting sand. Sometimes also you want to achieve a target recovery factor. Okay, in certain area of the reservoir, if you don't produce enough, you're going to leave too much oil behind, so that's also another factor that has to be taken into account. So one thing is that the main field, how I'm going to produce it to make my design, but then the definition or defining how much each well is going to produce, you have to take into account these kind of operational constraints, okay, or the reservoir characteristics and more things. That clear? Yes. Okay. So, and also remember that for the development process, or in the development process, the associated products, and these are gas and water for oil fields, or oil and water for gas fields, must also be taken into account. Okay. For example, if we have fuel oil, okay, usually the colors we use are green for oil. Okay, we use red for gas, and we use for water blue. Okay. So that's also important, because when we design the processing facilities, we make it for certain gas rate, okay, for a maximum gas processing rate and for a maximum water processing rate. Okay, that's so if by any chance, let's say, let's write that down. And Q water, okay, for a maximum rates available to process, due to, for example, water, the water treatment train. Okay, remember that water usually I have to treat it and I have to dispose it to the sea, so I have to have enough. The train has to have enough capacity to process it. Also the gas, the same thing. The gas, I have to have compressors if I have to export it. If I'm going to re-inject it, also I have to have enough capacity to put it back in the reservoir. And if for some reason, let's say I design my field, okay, with this, let's say I was expecting much less water, okay, this is the water maximum. Okay, let's say that it was here. Because initially I thought, well, my field is going to be like that. Okay, very, very low until the end of the life is going to reach. But then the real profile is like that. Sometimes maybe I neglected. There was more. The vertical permeability was higher than what I assumed or what I found, and I get this profile. What happens here? Do you think I will be able to keep producing that profile? No. Okay. What are the solutions here?
Shutting the wells.
That's one thing.
By water
Well,
injection.
one thing will be, to ask for some more money and try to make a change in my platform. But the simplest is to choke down production. Okay? And then I will be able to do it like that, but I will have to choke down production and use, for example, a lower rate. Right? Just because I'm producing too much water. So keep that in mind, that it's not only defining how much oil I'm going to get, what is the NPV, but I also have to be extremely careful with the associated products, if I have enough processing capacity to handle these products. And sometimes there is a big uncertainty in how these two are going to evolve. Maybe not on the main phase, but these depend very much, for especially water and gas, on the how close the water and oil contact is to the well, and how close the gas oil contact is to the well, and how the vertical permeability, how high it is. Okay, so there is big uncertainty in these profiles. and I have to take care of it. It cannot happen. It happened many fields that they are bottlenecked after producing for some years. They are bottlenecked just by water and gas. Okay, production of water and gas. And I think I had an example. It was one field. Let's see if I find it very quickly. Well, I can find it for next class. Okay. So for oil, these two, and for gas, but for gas, keep in mind that for gas, oil production is an extra source of revenue. Okay. And the value of oil is much higher than the value of gas. Okay, so if you are producing much oil, it can be an issue for many things. Okay, you have liquid in a gas pipe, a mainly gas pipeline. You start having slugging, you start having maybe some blockage, you start having all kind of ugly things. But at the end, that extra oil that is being produced is a very nice source of income. Okay, every extra barrel that you get of oil in a gas field really is going to change dramatically your economy of the field. Okay, so even though you say it's associated, it can be a bad thing. Actually, usually it's a good thing. It's a good surprise to get more oil condensate out of the gas. For gas fields, oil production actually it can change completely the economy of the field. Okay, usually for good. Water, on the other hand, is very dangerous. Water is, so let's put it here so you remember. Okay, danger, don't come close to it. For gas fields. Why? Because you have to know what is the source that the water is increasing, water production. But usually, if you have a coning aquifer on gas wells, these wells are going to die very quickly. There is no way that you will start draining. You know, the aquifer will always be there producing to the wellbore, and then you have no way, so you have, for example, the well, and you have here very low, you have an underlying aquifer, okay, and here you have the gas layer, and everything is going fine, you are a happy person, but then for some reason the aquifer depletion starts invading, and then it reaches the wellbore, and that makes a very big change, okay, on the pressure drop in the tubing, because before the tubing was used, well, I have just mainly gas with maybe some droplets of liquid, okay, of oil or water, etc. But then when I have this one, this is completely different. Remember, the delta P in the tubing somehow is the density of the mixture, right, times the H, the difference in height, times the gravitational acceleration, okay? And this field was usually used to produce with a density of gas that is maybe, how much? Anything between 80 kilogram and maybe 300 or 400 kilogram. But when water comes in, then I have a big change, okay? Maybe 10 times or 3 times, okay? 1,000 kilogram per meter. So that causes a very big pressure drop, and that causes that the rate starts to get very, very low, okay, and then the field dies. So be careful. Water in oil well is an issue for processing, but we still can produce for many, many, many years with a high water cut. Usually it can reach up to, we have fields, I worked in a field with 98% okay, water cut. It's only a water producer with some droplets of oil. but gas, no, not really. Okay, before we finish, plateau, so just one short comment. Plateau length for gas fields is usually something very long, between 10 and maybe 30 years, 40 years. And plateau length for oil fields can be something, it's usually very short. Okay, it can be from 2 years all the way maybe to 7 years, but that's like maximum. Maybe 2 to 5, that's more common. Okay, just you have, and I will have a short discussion next class on that, on why we have this big difference. Okay, just to close, we covered the decommissioning part that was missing from last class, the last part of the phase. Important, not our main focus on this course, but it's important to mention it. And then we talked about how the field behaves. There are mainly 2 production modes using this analog: constant rate or decline. And they are different. Why do we choose one or the other? They are different motivations, but usually plateau is for standalone, a field that I'm going to build everything from scratch: offshore structure, processing facilities, pipelines, everything. So I'm going to use plateau mode. And for decline, if usually satellite wells are very marginal fields of the small size that I want to produce to a neighboring field. And what else? That the associated products are important. In oil fields, usually they give me a lot of headaches, and in gas fields, usually I'm happy for oil, but no, I'm not at all happy for water. Okay, so I think that's all for today. So see you on Monday. Remember the first guest lecture. Okay, we're going to have it here, P13, and then we come back for the class.
Next week?
Next week.